Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So today's video for chapter 4, as the title is Motion in Two Dimension. In previous chapter, you've learned about kinematics, whereby you are concerned or taking look for velocity, position, acceleration for one particular axis only. For example, we are considering along x-axis only or y-axis only alone. Okay, but now, okay, when we talk about motion in two dimension, it means that we have to consider x-axis and y-axis at the same instance. So before we go deeply or details about velocity, acceleration and so on, so the most basic information that we need to understand is about position vector. What is position vector? It's actually a vector that having two kind of information, which is the R, symbol R initial and R final here. So let's say for the first position, the object is moving from position A to position B. The dashed line here is the path of the particle or object. So at position A, okay, at this instant or initial position, okay, it has R initial of position vector, where within the R there, if you still remember, this is polar coordinate. Within the R, you have the information of X and Y coordinate, Cartesian coordinate, at what angle. Let's say for initial is theta initial, so at theta initial angle. So this is for R initial. For R final, okay, you have the X and Y final information at theta final angle. Where is the theta final? Here. This is your theta final. Okay, so when you talk about position and you want to figure out the delta R, the change in position, okay, the change in position, or in this case position vector, okay, give you the information of the displacement. Okay, so information of this, the delta R, okay, from position A to position B is equivalent to R final minus R initial. As we know, when we use delta, it means that final minus initial. So R at B, in other words, minus R at A. Okay, so whatever information given to you, you have to make use of this. Alright, so we are talking about position vector. Regardless of the path, whether it's moving straight line, okay, or is moving in the path taken as this, in curve or straight line, okay, when we talk about displacement, is only consider final and initial point, regardless of the pathway taken. Okay, we only concern final point, final position and initial position, because this is the information of the change in position, or named as displacement. For velocity, velocity is defined as the average velocity is change in displacement over the time taken to have that change. Alright, so in other words, okay, this is for average. For in terms of formula, right, the R itself, recall the delta R itself just now is R final minus R initial. Okay, from position, for example, just now from position A to position B. This is the average. Regardless of path taken, is only consider final and initial point. However, for instantaneous velocity, whenever you have a limit of displacement, the delta R, to the respect of time, whenever your time is very small or approaching zero. In other words, this is derivative of R to the respect of t. For instantaneous velocity, okay, instead of taking derivative of the position to the respect of time, in technical method, you may also use tangent line. Okay, slope for the tangent line that particularly touching point A, because let's say we want to know, okay, the velocity at point A, okay, the direction of the velocity at point A. So okay, figure out one tangent line that touching point A, determine or calculate the slope of the tangent line for the A. That is the same meaning to this, which is direction or magnitude of instantaneous velocity. Okay, acceleration. For average acceleration, okay, is how big the change in velocity over the time taken to have that change. So v final minus initial over t final minus t initial. So if let's say the movement from point A to point B by taking this path, okay, so at point A, the object or particle has the r initial and v initial. For point B, the object has r final and v final, okay, at that instant. So the difference between this velocity will give you, over the time taken to have the difference to be done or take place, is equivalent to A average. Okay, so to have A average, the direction of the A average will be depending or according to the direction of your delta V. So how to get it in terms of drawing? It's V final minus V initial, right? So you have V initial, just imagine you can transfer it to this, and V final to this. Okay, but the case that you want to solve right now is V final minus V initial. So the V initial, you reverse it to this direction. This is negative V initial. So from tail to tip method, you will see from tail of the first vector to the tip of the second vector, this is your delta V, where your delta V is defined as this. Alright. For instantaneous acceleration, again, the same approach going to be used. This is actually by definition a limit of function V to the respect of time whenever your time is approaching zero or very small time. Two-dimensional motion with constant acceleration or uniform acceleration. So let's recall again, at any position, okay, the object or particle has the R position, where within the R it has X. How many X information, magnitude, times of unit I, okay, circumflex of I here, plus, okay, how many magnitude of J unit or circumflex here, right? So this is the information will be within the R itself. Okay, that is why we call it two-dimensional, because it consists of both of the information at the same instant. Right. So let's consider, okay, this situation given here. Let's say you have a park, a hockey park. Okay, initially A, okay, moving in straight line like this. Let's say hockey park on a field, okay, icy field, where you have no friction at all, and the hockey puck is moving along X like this, visualized like this. Okay, the horizontal red vectors representing the X component of the velocity are the same length in both parts of the figures, whether part A or whether part B. Okay, which demonstrate that the motion in two dimensions can be modeled as two independent motion in perpendicular direction. Why is it so? Why this segment is? Because like this. Firstly, let's imagine the hockey puck moving at a constant speed within X direction. And then, all of a sudden, you give a puff of air, okay, along Y direction to the puck, okay, to the hockey puck. Okay, what will happen? Okay, the air going to move the puck upward slightly. Okay, so movement to the upward, okay, is along Y-axis. It does not disturb the motion along X-axis. That is why we can say that, okay, motion in two dimension can be modeled as two independent. The keyword must be independent motion in perpendicular directions. Okay, so what does that mean by independent here? Okay, means that you can do the treatment, the calculation for x component alone and y component alone. The only things that they're going to share is time. The time involved within y component or x component is the same. Okay, so they can be calculated separately in simple. Okay, so within the V itself, okay, is defined as dr over dt. Okay, what is dr? Within r itself, you have xi and yj. So means that dxi over dt here, dx over dt along I here is your vx. Right? So this one is your vx. And this one is your Vy. Okay, as we know, for V, it consists of two information, right? Vx and Vy. So in terms of dx over dt, you can put it like this. So let's recall our previous kinematics equation. V equivalent to V naught or V initial plus Ax, isn't it? So that is the original formula. V, in your primary school, you have V equivalent to U plus AT, isn't it? So here, we are talking about the same thing because the A is uniform. However, okay, your V final consists of X and Y component. So treatment like this. So V final in terms of X component is V initial in terms of X component plus A acceleration along X component T. V final in terms of Y component equivalent to V initial in terms of Y component plus acceleration in terms of Y component T. So if you substitute this information to this one, right, you're going to have this kind of pattern of equation. Here is your X component. Here is your Y component. You may do rearrange, okay. You collect every single item of V in one parenthesis and every single item of AT in one parenthesis. Also can be done like this. So when you have this one or this pattern, this is actually in simple can be written as this one. V final equivalent to V initial plus AT. So within this you have xy component, within this you have xy component, within this you have xy component. But be careful, this equation only valid for constant acceleration or uniform or average acceleration. This is not valid for instantaneous acceleration. Alright, so now if we refer to the other kinematics equation, delta x, this is a previous equation is delta x equivalent to ut plus half at square in terms of x, right, in terms of x. If you want to refer, this is delta y equivalent to uy t plus half ay t squared. Right, so this is the same thing. We just now, within the delta, you have x final minus x initial, right? So you bring the x initial to this position, to the right side. Left alone, on the left side is the x final. Goes the same to this. Within delta y, there is y final minus y initial. So you rearrange the y initial, you bring to this side. So you will left with y final at your left side of this equation. So it's the same thing, just rearrange. And recall that r, okay, r equivalent to, or x just now is the r. isn't it? Because R itself is X and Y. Okay, or you can simply put it as XI plus YJ. This is a thing. Okay, so within the R itself, this is information of your X, right? So this is your X final. The whole bar of this is this one. The whole bar of this is this one. So this one. This one. Okay, I hope this is clear. And what happened to this level, it is actually just rearrange. Okay, rearrange in terms of the same item. Let's say for the position, the X and the X, collection of the X. And then for the V, collection of the V. Then one, collection of the A. So you can simplify this into the term of this. R final is actually R initial plus V initial T plus half AT square. Bear in mind that R here consists of these two information. V here consists of these two information. And A here consists of these two information. Alright, so what we have in our hand just now, we have this equation and this equation, okay, where we have a constant A. Bear in mind, it's constant or uniform or average A only, not for instantaneous. So in terms of drawing, what are we doing here? It can be manifest in terms of this drawing. So what we have here, okay, this is V initial, this is AT. Okay, so from tail to tip method, from the tail of the first vector to the tip of the second vector, you're going to have your V final. This is the meaning of this, the situation here. Okay, this one is manifest in terms of this sketching or drawing vector. Alright, for this one, okay, R final equivalent to R initial plus V initial T plus half AT squared can be interpreted or sketched in terms of this diagram. Right. So what are we doing here? This is your R initial. Okay, move to the VIT second vector. Move to the third vector, half AT squared. So from tail of the first vector to the tip of the third vector, the last vector, is your R final. So this is the meaning. So in terms of components, okay, for this one, okay, it has Vx initial, right? You have Vy initial. In terms of AT, you have AXT. In terms of Y, you have AYT. So means that when you want to do the summation or mathematical treatment, you are going to sum between Vxi initial AXT to have Vx final. That's the meaning in terms of sketching. To have Vy final, you have to add up Vy initial plus AYT. Back to this equation, right? It's just that everything here along y-axis, everything here along x-axis. That is why we can say that the two-dimensional motion can be treated as single or separately. Goes the same for this part and this part. So example 4.1, a particle move in the xy plane starting at t equivalent to 0 with an initial velocity having an x component of 20 meter per second. So here is the Vx. So here is information of Vx. Okay, initial. And y component of, and here Okay, y component velocity of negative 15. So we can put v y initial is negative 15. Right. And then the particle experiences an acceleration in the x direction. We only have ax given by this information. So this one is only ax. Alright, so to visualize the situation given in terms of statement here, you can have the reference axis like this, and this is your object moving initially, okay, with the v. Your initial v is in this direction. So it consists of two information, vx, which is positive, vx initial is 20, and you have component of vy initial equivalent to negative 15. Why is it negative? It's pointing downward. Okay, the object is moving, okay, to the right but downward as well. So the first part, determine the total velocity vector at any time letter. Okay, so how to do this? Okay, you have this information in your hand. Okay, how you know that ay is 0? Because just now it has only a along x, already stated. Okay, so by making use of the first equation, v final equivalent to v initial plus at, okay, not to forget within each of these you have x or I and j information. Alright, so you have v initial in term of x is 20, a in term of x is 4 times with the t. You don't know yet the t. Sometime later, right? It is not stated. Is it 5 seconds? Is it 7? Is it 10? Not yet. Just after a few time, a time later. And then negative 15 of vy initial plus ayt, but then ay is 0. That is why finally your v final expression or equation is equivalent to 20 plus 40 everything in I unit minus 15j units. Okay, bear in mind what does that mean? This is along x, this is along y again. Then B, calculate the velocity and the speed of the particle at t equivalent to 5 seconds and the angle the velocity vector makes with the x-axis. V final, we already have this equation just now. Okay, now substitute the t of 5 seconds to the formula. You will get this as your answer. And the direction, because it asks for velocity and speed. Okay, so velocity consists of two information, magnitude and direction. So this is the direction, which is tangent theta equivalent to vy final over vx final. To have theta only up tangent of these things, so substitute negative 15 vy final and 40 is your vy initial, vx final. So finally you will get negative 21 degree. What does that mean by negative? Okay, it means that it's below x-axis. Okay, so remember the path taken like that, right? If let's say here is the position after 5 seconds, so consists of, okay, vx here, vy here. So the angle is this one. This is the theta that you calculate here, right? This is the yellow theta there. That's the meaning. Magnitude, in terms of magnitude, okay, v final, okay, the magnitude of it, when we use modulus here, means that we are concerned about magnitude. So Pythagoras, square root of, then you will get, this is the answer, the speed. Okay, the speed as the magnitude. right? C. Determine the x and y coordinates of the particle at any time t and its position vector at this time. So coordinate means that you are going to use R formula. Okay, you have this one. Then every single thing has components. This is all of it in terms of I, in terms of J. Then substitute the information. R initial, okay, in terms of x is 0. Okay, 0 as well because it starts from origin. And then it's 20. Okay, this is AX. This is AY. Then you're going to solve for this one. You're going to have, this is your R final formula. What if we wait a very long time and then observe the motion of the particle? How would we describe the motion of the particle for large value of time? It's a very long period you are going to observe this. The path become more and more parallel to x-axis. Okay, parallel to x-axis. Okay, because of this equation. Nothing changed within y component. Alright. So now we're going to move to projectile motion. This is slightly different compared to motion in 2 dimension just now, because motion in 2 dimension just now, we might have AX, we might have AY at the same instant, or we might have one of it 0, just like the example 4.1 just now. However, when we talk about projectile motion, okay, this is a bit special because how to have projectile? What does that mean, projectile? Normally, you have an object is projected upward, okay, in the air. Okay, it's projected upward in the air. Whether the perfect case is going to take a parabolic path like this, or it could be any kind of pattern. For example, it could be from a building. Okay, we throw something moving downward like this. Okay, this is a building, let's say. Or it could be from a building as well. It's going to move like this. So initially, the V is along X only. Okay, there is no V initial along Y. For this case, both of it you do have. Okay, V initial along X, V initial along Y. Okay, what else can we have? A situation is from certain height, let's say above the ground. Okay, you have an object and then the object is tossed down like this below x-axis. So from here, the V X initial and the Vx initial, here Vx initial, here is Vy initial has negative sign because it has direction downwards. Okay, for this one it's positive. How about Vy initial? 0, because the motion initially completely horizontal motion. For this case, Vx initial positive, Vy initial also positive. Alright, so many other patterns or method. The most that you're going to see this one. Okay, a perfect case, parabolic path. Okay, semicircular. Okay, for this case, let's say, alright, starting from point A up to point E, okay, the object is moving along a circular path or parabolic or semicircular path. Okay, parabolic path. Okay, at this initial or instant, okay, it has Vx initial, it has Vy initial. Okay, at this V initial, this is the solid vector and certain angle at the starting point or origin. And at any position, okay, it has both still Vy, Vx initial. Why is it still Vx initial? Okay, there are few assumptions needed to be justified or used, okay, within projectile motion, a special case. First one, we consider the x component of the velocity remain constant because there is no acceleration in the x direction. Okay, why is it so? We consider there is no friction at all, no air friction. So when you have no air friction, just imagine like you are moving, right? You are moving to the front, to the along x direction. Let's say you want to run along x. You are running along x direction. You're going to feel the air, isn't it? Going to oppose your motion. The air going to give you friction. Okay, for this case, we consider there is no air friction, equivalent to 0. Therefore, you can maintain your V along x. Okay, no changes, right? That is the meaning of this one. Okay, and then second assumption needed is the y component of the velocity is 0 at the peak of the path. Why is it so? If you see here, the vector Vy getting smaller compared to this one. When it reach maximum height, okay, the object going to be in velocity of the object in term of x component only. There is no Vy at maximum height. With condition, this is okay, H maximum. If you still remember, okay, this is similar to the free fall, isn't it? The free fall. Okay, maximum height, if you throw something, free fall, if you throw something and then isn't it? So at maximum height, the V here 0, right? Okay, so the same case to this. Okay, so means what? It means that we are going to treat the y component as free fall case. Okay, then the ay is always equivalent to negative g. Okay, ay always equivalent to negative g. Ax always 0. This is the important assumption in projectile motion. Okay. So in terms of understanding of the vector, okay, what are we doing here? Okay, let's say an object moving from origin and back to the ground. Let's say from point A to point B here. Okay, so at any instant, the r position vector final, okay, at any instant, yeah, at this position perhaps, for example, okay, is equivalent to r initial plus v final t plus half at squared. However, the a that we have here only along y, which is the g, right? And then the v final you consist of two things, x and y component. Okay, the r also you have two things to be considered. In terms of drawing, what does that mean by this? Okay, in terms of vector drawing, your r final, okay, is actually resultant of, okay, your r initial, for this case 0 because it's starting from origin. This one 0, referring to this figure, yeah. Okay, plus, okay, v final, okay, v final t, right, plus half gt square. This is supposed to be v final t. Okay, this is v final t, right? Then at any instant for vx initial, okay, vx initial is actually v initial cos theta initial. Vy initial is actually v initial sin theta initial. Where to place this one when you want to figure out this one? Okay, why is it cos? Why is it sin? Okay, because let me redraw. Okay, this is x component, this is y component. This is your motion, let's say path taken by your object. This is your v initial. Okay, having theta initial here. The component of the v initial along x is here. This is vx initial. The component for y is here, vy initial. So, to have vx initial, okay, is gonna be making use of this information given. Okay, to the respect of this angle, you are going to have vx initial, v initial cos theta initial. To have v y initial is going to be v initial sin theta initial. That is why. Okay, how about x? Okay, based on formula, x final equivalent to x initial plus vx initial t. This one. Okay, you may now use as well this equation and this equation and this equation. So many, right? So it depends on what given to you, what you have in your hand, what information or unknown needed from the questions, okay, and how you can manipulate. So this is in terms of y. Where is the x component? Only this one. Why is it so? Because ax always 0. If you substitute to this equation, you will get vy, vx initial equivalent to vx final. If you substitute to this equation, whereas here, okay, you will get x final equivalent to x initial plus this one, right? Vx initial t. You've got no ax. Okay, and then if you substitute to this one, ax also 0, you will get v final x equivalent to v initial x. Okay, so in conclusion, okay, memorize this one. Ax equivalent to 0, so vx final equivalent to vx initial all the time. And another one is ay always equivalent to negative g. Why is it negative g? Recall back in your free fall. Okay, the g always downward. The initial point, the starting point as our origin or reference point. So at initial here, your v initial along y is upward, whereas okay, your g is downward. Right, how about if it is already falling down part? Okay, if it is already falling down part, okay, let me show you why is it become negative as well. If let's say you consider falling down part here, okay, the vy is downward. This one is downward, right? The g also downward. Vy is downward, negative direction. Because of what? To the respect of y-axis. Equivalent to in terms of g. So at the end of the day, vy equivalent to negative g as well. Right. Horizontal range and maximum height of a projectile. Okay. This is your v initial. Remember, v initial has components. Here is vx initial equivalent to v initial cos theta initial. Here is your y component, v y initial equivalent to v initial sin theta initial, right, at any instant. Okay, it has the component of it. Recall here, so you have component, and then at maximum height, okay, vx axis, x final equivalent to vx initial. However, vy at maximum height is 0, okay, because we treat it same to free fall case. Okay, it stop a moment before it fall down, right, for free fall. And then at this instant it has component again, right, and then the moment it's strike the ground, it has V final here, okay, and it has component, okay, V final X, V final initial, then it has theta final here. Okay, so the maximum range, the maximum R, the R here, we call it range. This is actually X maximum, okay, or this is actually your delta X, displacement along X. Okay, if starting from here to this point, okay, what is your delta Y? Will be 0, because the same level, right? Okay, the same level. So along this path from origin to B, okay, delta Y is 0. Okay, the only thing that going to be shared between Y component and X component is time. T along X is the same T for Y component, which is only T. Okay, so if let's say you have two unknowns within Y component, means that you need to solve for X component, figure out the T and substitute into the Y component. So about the height just now, based on this formula, okay, if you are talking about from origin to point A, so V final there will be 0 here, this one, so this one, and then this is your Vy initial. Vy initial is this one, okay, and then why is it minus GT? Supposedly Vy final equivalent to Vy initial plus Ayt, right? Why is it negative? Okay, because we have the conclusion or assumption that Ay equivalent to negative G. Okay, then next one, rearrange this equation because we want to know what is the time at maximum height. What is the time in flight until it reach point A, maximum height. So rearrange the equation, you will get this equation for T. Alright, time taken, T to move from origin to A, supposedly the same to the T moving for the movement from point A to point B. So okay, the T here and the T here supposedly the same T. You can prove by your calculation, okay? And so in terms of Y final, the height, okay, maximum height, maximum, yeah, okay, is equivalent to, okay, this is your, here is 0. Why is it 0? It start from origin, 0, 0. And then this is your Vy, this is your T, and then this is your original G as the Ay, and the whole bulk of this is T again. Moment, this is the T, so this is your T, right? Then you will have to use slightly by using trigonometry identity. You will simplify this equation into this. Whether you want to have it from start or you want to memorize this one, is up to you. Okay, I leave it to you. In terms of X, okay, we have this formula only, and R is the range, okay. Where's the A? Supposedly we have delta x equivalent to Vx Vx initial t plus half Ax t square, right? The initial formula. But then, as we know, Ax 0, because all the time we assume Ax equivalent to 0. Okay, that is why the formula only left with this one. So this is your X initial. Okay, the T to move from origin up to point B, from origin up to point B to have the range, right? So it's actually 2 times of the T to move from origin to A. That is why. Okay, so T total, yeah, here. T total in flight, we call it. Alright, so here is your V, this is your T, again, this is your T, okay, and here is just now is your VXI initial, right? So if you open up, you will get this kind of formula. This is trigonometry identity. Substitute here to simplify this function. You will get this one. So it's up to you whether you want to memorize or you want to derive it from the start. It's up to you. I leave it to you. Okay. Okay, trajectory of a projectile. So the trajectory of the projectile motion, okay, from origin, okay, you can have many angle projected, right? So basically, okay, sometimes in calculation, let's say, for example, if you see here, whether it's projected at 15 degree or at 75 degree, okay, the delta R is the same. The delta X is the same for this case and for this case. For this case, for 15 degree or 75 degree of theta initial. So when you do, same goes to this one, right? Okay, and this one. See, the R, the yellow R is the same, isn't it? Means that you may use 2 angles, okay, to reach the same R. What does that mean in terms of math? Whenever you do quadratic solution, right, you might have plus minus, isn't it, as the option for angle. Okay, if you have 2 angles from your solution, this is the meaning. You may use the 2 angles to reach the same range. Alright. Okay, so this is my advice for problem solving strategy of projectile motion. You need to have a sketching firstly, the free body diagram of your object, okay, and the path taken. Sketch as well the velocity initial of X component and Y component. You may put your assumption Ax equivalent to 0, Ay equivalent to 0 from the beginning, and also the reference axis. Okay, then figure list of the information for the X component and Y component given to you. Then figure out which kinematics equation suits the best to solve the unknowns asked in the question. Always bear in mind that Ay equivalent to negative g, Ax equivalent to 0. The only thing that they share is the time. Example 4.2, the long jump. A long jumper leaves the ground at an angle of 20 degree above the horizontal and speed of 11 meter per second. Okay, so for a long jump process, the path taken will be similar to the one that we discussed just now. It's gonna be semicircle, isn't it? like this, the path taken. Right? How far does he jump in the horizontal direction? Means that R is asking for R. So the formula that derived just now is this one. Substitute every single things. Okay. Then you will get 7.94 meter in terms of X. Where is this one? It's here. 7.94 meter. That's the meaning. Okay, part B. What is the maximum height reached? Maximum height. Okay, this is a formula. Where is the maximum height? So if let's say this is path taken, maximum height here. Okay, so this is your H. Okay, it's 0.722. You may use this one, or you may also start from information of V, Y at this instant is 0. Let's say you're going to do, you have the V initial, right? You have the theta initial, 20 degree, V initial of 11. Okay, so you may also solve by using Vy final equivalent to Vy initial plus Ayt. Okay, provided that you have the T already lah in your hand. Okay, or you may also use to figure out the T, and also delta Y, which is the H that you want to solve. Okay, is delta Y equivalent to Vyt plus half Ayt squared. Okay, so here you know V final at maximum height 0. From this, and your Ay is negative G. From this, you're going to solve for your T. Right? Once you get your T, you may substitute here. Okay, substitute your T here. And your T here, this is your negative G. You may now figure out your H if you don't want to memorize this equation. Right, 4.3, a bull's eye every time. Oh, very good. Okay, in a popular lecture demonstration, a projectile is aimed directly at a target in such a way that the projectile leaves the gun at the same time the target is dropped from rest. Show that means that proof. The projectile hits the falling target as shown in figure. So, the velocity of the projectile, red arrow, changes in direction and magnitude, but its acceleration, purple arrow, remain constant. This is the G. Okay. So, let's see how to prove that one. Don't worry. The proving question won't be as one of your final exam question. Okay. So, for this one, this is delta Y initially, V naught Y plus half Ayt squared. Okay, you have, why is it tangent here? Why is it tangent here? To have the, here, okay, here is the diagram. Okay, so if you see here, the line of sights, okay, the line of sights, you have theta angle covered within. You have xt, x target, okay, and then you have the height here, okay, is h, is xt tangent theta. What does that mean? You have your angle here, okay, you have your x here, and this one is your y, okay, y initially, but you make use of this theta initial. So this is actually xt tangent theta is your y initial, right, by make use of the triangle, right? Then, okay, what we have here, okay, This is the target. This is the projectile for projectile part. Okay. Y initial is starting from origin. That is y is 0. Okay. Then you have y projectile, vy initial of the projectile, which is vy initial sin theta. Why is it sin? Okay, as we derived before. Okay, this one is this one. Right, and then what else? For x component, here is this one. Okay, we've got no ax, so we don't have to use the formula exists of for ax. So rearrange the equation of this. You will have the t as your unknown. This t is substitute into a y formula. You will have this equation with p. Okay, so here is xp, this is your t. Substitute only for one part, and then you have to simplify this one. To simplify the sin over cos, you get tangent theta. Okay, and then this one cancel out each other. This one finish. This one and this one become tangent. Right. So you have simpler equation. Example 4.4. A stone is thrown from the top of a building upward at an angle of 30 degrees to the horizontal with an initial speed of 20 meters per second as shown in the figure. The height from which the stone is thrown is 45 above the ground. Okay, so if you see the situation here, this is actually similar to the free fall. But the free fall is from here like this, isn't it? We ignore this one. Okay, but now, okay, the real case right now for projectile motion, okay, we do have the delta x. Right, so how long does it take the stone to reach the ground? So this is the total time taken from starting, okay, until it reach the ground somewhere here. Right, so if you see solution here, you are using x initial equivalent to x final, x initial equivalent to y initial equivalent to 0, okay, and y final negative 45, okay, meter, because it's below the origin. Why? Because of this. Okay, your starting point is somewhere here already. This is your y-axis, this is your x-axis. Okay, so the motion is this one. So it's already, this is origin. Here you have whatever the x is, delta x is, and negative 45 below, because it's here to this is 45 meter. And why is this one 0? Starting at origin. And then ay equivalent to negative g, v initial equivalent to 20. Let me add up one more, which is ax equivalent to 0 all the time for projectile case. So vx initial equivalent to v initial cos theta. Why is it so? Initially like this. Okay, so the component of it here, this is vx initial, this is vy initial. So to have vx initial, okay, vx initial is vi cos theta. Where's theta? Theta here. Okay, and then vy initial, v initial sin theta. Right, so next step will be delta y equivalent to vy initial t plus half ayt squared. This is actually, originally the formula is this one. by substituting the AY equivalent to negative G, you will get this kind of pattern. Within delta Y, you have Y final minus Y initial, right? So delta Y itself, negative 45. Be careful, negative must be included. Okay, is vector. Plus, equivalent to 0 plus. Okay, why is it 0? What is 0? Here. This one. Okay, this is Y final. Okay, the 10 meter per second. What was this? This one, right? Which is this one. Okay. Then you get your T equivalent to 4.22 second. B. What is the speed of the stone just before it strikes the ground? Just before it strikes the ground. So V final means, okay, remember again, right? This is your y-axis. This is your x-axis. So your object moving from this to this. Okay. So at this instant, still have V. The moment is going to strike, it has V here, V final here. Okay. So in terms of Y component, this one, okay, by make use of the T taken from starting until it reach the ground, 4.22 second, you have negative 31.3 meter per second. And how about Vx final? Why there is no calculation given for Vx final? Because the Ax is 0. Therefore, Vx final always the same to the Vx initial. Okay? Because of the formula, let's say Vx final equivalent to Vx initial plus Axt. You see? Proof by that. Then you have to use a Pythagoras because it's components, right? So by make use of the Pythagoras, okay, what is the final answer? Oh, forgot to put. Okay, please calculate this one. You should get your final answer. Okay, okay, by calculating this. The question asking for speed. Speed. That is why no need to do theta or tangent theta. Okay, what if the horizontal wind is blowing in the same direction as the stone is thrown and it causes the stone to have horizontal acceleration of positive 0.5 meter per second? Which part of this example, A or B, will have a different answer? Okay, the time does not change. Okay, why is it? Let's say we consider the A now, positive 0.5 meter per second squared. So you have this equation, you will calculate your Vx final 19.4. By using Pythagoras, okay, this one, you see, there is no effect, okay, in terms of time. Time does not change, right? Because of what? To have part A or B, look at part A. Look at part A. Okay, part A. Do we use any AX in our solution? Do we use any AX? Here we don't have the AX formula. Okay, right? It's only Y component, right? To have the T. Okay, so the T does not change even though we do have AX right now. Okay, in calculation of your part B will be different because now you have your Vx final. So you repeat the same calculation of Pythagoras again, you will get this amount. So your final speed will be larger. 4.5. The end of the ski jump. Okay, a ski jumper leaves the ski track moving in the horizontal direction with a speed of 25 meter per second as shown in figure. Okay. The landing incline below her falls off with a slope of 35. So where is the 35? It's here, interpreted here. Where does she land on the incline? Or also the slope is this one. Okay, that is the meaning. So be careful, because the person is landing not on the horizontal surface. In our previous example, let's say towards from here, okay, like this, isn't it? So the path taken here, and here you have a level, okay, straight line, horizontal. But this case is she land here where it is on the incline. Alright, so we need to be careful. By the way, initially this person, the jumper, having initial velocity only in terms of x component, because moving in horizontal direction only. There is no component of the vertical. So 25 meter per second here is only v initial. Is also the v initial in term of x. V initial in term of y is equivalent to 0. Okay, and what else assumption needed? Ay equivalent to negative g, ax equivalent to 0. Let's move to the solution. So if you see here, right, x final is d cos theta. Where's the d? Here is the x. Okay, d cos theta cos phi. And y final at this position consists of x final and y final information, right? This is origin, x initial, y initial. So alright, it's negative d sine phi. Why is it negative? It's pointing downward or below the origin. Okay, then x final equivalent to this. Where is the why is it no a? The original formula is this, is actually delta x equivalent to vx initial t plus half ax t square, right? But 0. That is why it's become or left with this. Okay, so you substitute the x here with this one. Right, you have the second equation. Then you have the y, similar approach to this. Okay, why is it negative? Because of the ay equivalent to negative g. And then you have d sine theta equivalent to negative half gt squared. D sine theta here, okay, is your y, this one. And v initial of y is 0, because it's completely moving initially in terms of x component. That is why you are left with this equation. Then rearrange, okay, equate between this equation, okay, and this equation, right? Substituting the t as our interest, okay, so you will have this kind of, you might need to use some sort of information or prior knowledge on trigonometry a bit. Okay, you have t 109 meter, you have x final equivalent to 89.3 meter, y final equivalent to negative 62.5. If let's say you are not comfortable with the trigonometry step here, okay, you may calculate for the t, look for the t, and then use it in terms of value of it, and substitute to the formula and calculate step by step. No need for you to put it in terms of trigo like this and get crumple here, please. Okay, do what suit you the best, right? Suppose everything in this example is the same except the ski jumper is curved so that the jumper is projected upward at an angle from the end of the track. Is this design better in terms of maximizing the length of the jump? Okay, this is not good design. Why is it so? Because now, okay, what does that mean by the statement here? Now the jumper going to take this kind of path, okay, instead of this one horizontally initially. So it's going to have both Vx initial, Vy initial. So when you jump higher, you have the two components, okay, you will take a longer time actually. Okay, so in general this is not a good design. Longer time means that shorter in terms of x, right? So it's just like diagram given here. Okay, so to have a maximum with the same initial velocity, let's say 50 meter per second, to have maximum range, okay, the best is 45 degree as your theta initial. The bigger the theta, you see here, the shorter the range. Okay, but this is in general. But for this case, quite special because it land on the incline. It's not landing, she is not landing on this horizontal surface. She land on the incline. So kind of special bit. So we need to somehow do the particular calculation. But then in simple, this is not good idea because the higher you projected yourself from the origin, the shorter the R. Okay, in terms of proving of calculation, you may see here, okay, now if you take this path, okay, you're going to derive, right, the X and Y formula, substitute the G, okay, the same approach, figure out the T, okay, and then followed by, okay, solving here, okay, then you will see the theta is 27.5 degree, okay. Which theta is this? This theta, the theta here, okay. Or you can simply, if you don't want to dizzy with all the trigonometry identity, you can simply imagine it's like this is the situation, just like the figure is rotated because this one is inclined. Okay, so here is the starting point. Okay, here is your X, your Y, your D, okay, and your angle here, your theta. Okay, theta somewhere here. Your x-axis, your y-axis. Okay, similar approach to that.